Okay, let's start. Yeah, I mean, since first I want to start from where we have left yesterday. I mean, the expression of the nuclear matrix element that should be calculated, that then will appear inside the definition of our half-life, inverse half-life. And here I wanted somehow to decouple, I mean, rewrite the expression and decouple the elements that appears inside the summation in order to point out that there are some issues that today we are going to consider. First, we have the part that is related to our calculated nuclear wave function of both the initial and final parent and daughter nuclei, and also with respect to the intermediate states of the daughter nucleus. As I pointed out yesterday, that term that I mean is merely how is it constructed your wave function, and then you calculate this one-body transition density matrix elements. First of all, this means that first you need to diagonalize the nuclear Hamiltonian. Nuclear Hamiltonian, the eigenvalue of the nuclear Hamiltonian can be very schematically written as follows, where the nuclear Hamiltonian is something very complicated because you have obviously a one-body term that deals with the kinetic energy of all nucleons, and this is a one-body operator. Then you have the two-body interaction among nucleons, and you have to consider all possible interaction among all possible nucleons. Then in nuclear physics, we need also to consider eventually a residual three-body interaction, because as I pointed out already yesterday, the nuclear Hamiltonian is not a fundamental one. Namely, is an effective manifestation of the strong force, where nucleons are considered as point-like particles, but we know that they are not. Okay? So the nuclear interaction is naturally an effective one. And this means that if you want to start from the expression of the strong force in QCD, and you want that a force that explicit among quarks, gluons, into something that works among nucleons. This is something like considering the Coulomb force for systems such as molecules, and then you construct an effective force that is the van der Waals force that explicates among molecules. So the van der Waals force stands to the nuclear forces, like the electromagnetic force stands to the QCD. Okay, but this doesn't mean that we are not only considering a two-body potential, but in principle, you should, in order to have a proper description, you need to consider a three-body force and a body force if your system is an a-body system. Our knowledge on nuclear physics for a long time, I mean, since the 1930s, of the past, the 30s of the past century, we know that the main component, something that is the main component of the nuclear Hamiltonian, is the two-body one. However, there are some residual effects that could be very, give you some specific refinements to your to the properties of nuclear systems that deals with the a three-body term, at least. Since we are speaking about the nuclear Hamiltonian, it's worth to make a few considerations. First of all, probably you know that the two-body component of the nuclear Hamiltonian has a very, very peculiar behavior. Namely, in terms of the distance among nucleons, the nuclear potential is something like goes like this. Namely, you have a short range region where this is approximately 1 Fermi, where you have a very strong repulsion. Okay? This is something that makes your life very hard. Because in the earliest version of two-body forces, theoretical two-body forces, I'm speaking of, for example, the so-called Amada-Johnston, this famous one, a potential that was able to reproduce data of the two-body system with in a very efficient way. Then this region was schematized as an hard core, namely an infinite potential, infinite repulsive potential. So you can imagine to manage something like that is very complicated. Okay? But I will come to this later. Then obviously there has been some evolution in the sense that we had a more systematic approach to the description of two-body forces in terms of meson theory. Nowadays I'm speaking about the last 25 years or something like that. There is a new approach to the description of, to construction of nuclear Hamiltonian that is based on chiral effective field theory. Namely, through effective field theory, we are establishing a link of QCD and low energy nuclear physics by performing a perturbative expansion of the nuclear Lagrangian in a way that is nuclear low energy Lagrangian that is consistent with all symmetries of QCD. Okay? And this approach, systematic approach to nuclear forces, it's very elegant because what you can obtain from this chiral perturbation theory expansion is not only the construction of a two-body potential, but of a consistent three-body potential, consistent four-body forces, and so on. And what happened? Only in terms of degrees of freedom of interaction between nucleons, in terms of pions or deltas. Okay? So low energy degrees of freedom. This is something that has become quite appealing for our community because now these terms are not something that you try to construct through meson theory and then fit all the coupling constant on the experiment and so on. You still have to do it in effective field theory because they appear some low energy constant. But what is very interesting is that the set of low energy constant that appear in the construction of two-body forces are the same. Most of them, they appear also in the construction of three-body force and so on. So all components of the nuclear Hamiltonian, they are consistent each other. Okay? And moreover, this potential, they don't show this repulsion because this is integrated out thanks to the effective field theory. Okay? So they are smooth potential, no longer dealing with this strong repulsive behavior, and they are consistent with the symmetries of QCD. Okay? So any question about this, or did you ever heard about this evolution of our understanding of nuclear forces? Probably not. I know. Sorry, I'm coming to you so I can hear you better. Yes. No, it matters. Yeah, it matters. Let me, in a few steps, I'm going to tell you why it matters. No, you're right. My point is that since we are writing the nuclear Hamiltonian, it's worth to discuss each terms that appears inside. Okay. Then in a few minutes, I'm going to tell you why this repulsive core matters and how much it matters. Okay. Yeah, sure. Correct. No, no. Usually they are accounted for. Okay, but there is a few order of magnitudes between the role of electromagnetic residual force and the nuclear one. That is, I mean, much stronger. I mean, I would be happy to deal only with the problem coming from the electromagnetic. All of us, we account. I didn't mention obviously the Coulomb force here, but yeah, but this is not the main trouble of our problems. Okay, even if there are some specific features of nuclei that experimental they are investigating and trying to see if and how it's relevant to a proper treatment of this electromagnetic. But I mean, yeah, I mean, for our problems, no, you're not neglecting it. You are considering it. I'm not saying no. This is the main part, and no, it doesn't happen. It means only that it's not an issue. You can think about that. Sorry, the electromagnetic force is already accounted in this two-body term. Think, no, consider something like that. In fact, how do you just open, a small interval? How do you construct this potential that are effective one, and namely they depend on some low energy constant, low or high energy constant, depending if you are dealing with Meson theory and so on. What you do is to fit phase shift data of nucleon scattering. Okay, so but as you can imagine, it's difficult to gather many data from the neutron-neutron scattering. Neutron-neutron is purely a nuclear interaction, okay? Because there is no effect of the electromagnetic force. But what are we doing? We are considering the proton-proton scattering mainly, or proton-neutron scattering, because you need both channels. The isospin 1 channel of identical particles, and the isospin 0, namely neutron-proton interaction. Okay? Then once you have extracted your data phase shift from the proton-proton scattering, what do? You clean it from the role of the Coulomb force. But this is very easy because Coulomb force can be solved exactly at whatever degree of accuracy you want. I mean, so, okay? Okay. So, now coming back to our Hamiltonian, as I mentioned it yesterday, this Hamiltonian presents many complications. First of all, you have the main, let's for a while neglect this one as a residual problem, okay? Also because let's say that if you have a hardcore potential this term is very, very small, irrelevant. If you are dealing with this new class of nuclear Hamiltonians, namely those derived in terms of the effective field theory, where you smooth the role of the two-body force and this behavior is no longer like this, okay? What happens is that you have to pay a price. Somehow you are shifting your hardcore problem into irrelevant three-body potential. As a matter of fact, in nuclear structure calculation, what happens is that these terms, these three-body terms, they contribute as repulsive, a repulsive contribution. Okay, this is quite clear if you do an analysis of the problem of the equation of state of nuclear matter. I don't know if you ever met this problem in your studies. Okay, let's forget. I mean, but infinite nuclear matter that is important in order to describe the structure of neutron stars. It's a very good environment to study the properties of the nuclear Hamiltonian. Usually, I teach my student from nuclear, the equation of state of nuclear matter, because you understand many things. Okay, this is an hypothetical environment, infinite nuclear matter, but I mean, you can really understand many things about the nuclear force trying to derive this equation of state, okay? Okay, let's stop and let's come back to our Hamiltonian. So, as I said, analytically, exactly, you can solve this, diagonalize this Hamiltonian only for a very few systems, namely 3 and 4 body system, okay? That's it. Whatever you do elsewhere, increasing the number of A, is an approximation. However, there are some methods, like the one that we call a few body methods, that where the approximation that you are considering, they can be controlled within a very good theoretical error, let's say up to A about 12, okay? So let's say that from nuclear models that consider the physics between A equal 4 and A equal 12, they are almost exact, okay? But from 12 on, where most of nuclei that are of experimental interest, you need to deal with many body methods. Many body methods that necessarily need some kind of ansatz, some kind of approximation, and what people they are doing is to improve these many body methods or construct new one in order to have under control the theoretical error. Again, there is another problem, namely, as I said, the potential is an effective one. What does it mean from the theoretical point of view to have an effective Hamiltonian? It means that different two-body potential can give you, in nuclear structure calculation, the same set of eigenvalues. So they are all equivalent somehow on shell, but their off-shell behavior can be completely, it's not controlled by the transformation that construct your nuclear Hamiltonian. Then the wave function can be completely different. So that's why those one-body transition density matrix elements can be completely different, and your results are different, as I showed you yesterday with that plot. Okay, that's the main reason. So what does it mean, this? That dealing with many body problem, as you deal with an effective Hamiltonian, then you need to construct consistently effective transition operators. that compensate this the role of having different wave functions for different models. I'll come back to this point. Now, let's classify the many body models into general categories. One is mean field and the other one is what I call microscopic nuclear models. Now, let's list some of them. You can have the energy density functional approach. Namely, you construct an energy density functional that it is able, through an artifact calculation, to fit the masses of the whole nuclear chart. Okay? Since this is a one-body problem, because we are dealing with a mean field Hamiltonian, this is quite an approach that is very easy from the computational point of view. Okay? And if you do remember that, let me open again. Okay. It appears there. This is one. Another one is the quasi-particle approximation. And another one is the interactive boson model. Now, all these methods, they deal only with some of the most important features of the physics of nuclei. Namely, for example, the quasi-particle random phase approximation deals with the fact that one of the most important component, especially in the low energy part of the nuclear spectra, excitation spectra, deals with the so-called pairing interaction, an interaction that is like similar to the phenomenon of superfluidity or superconductivity, namely pairs of identical nucleons, they are coupled to total angular momentum J equals 0 plus, okay? Knowing this, using the quasi-particle random phase approximation, you are going to move from the picture of nucleons as particles to quasi-particles. This makes the calculation quite easy to be solved, almost analytically through a set of coupled equations. But you have very few parameters that come into play, and very few how can I say, correlations that you can take into account with this method. So it's very simple to solve for an A-body Hamiltonian, okay? But then you have the ability to have a predictive system with with especially it appears in a parameter that is called GPP that usually is tuned both to fit the spectroscopy, but at the same time also the Gamow-Teller transition, because Gamow-Teller transition are both strongly dependent on are strong parameter. So it makes life very hard in order to understand if the fitting of this parameter is influencing mostly the Gamow-Teller transition or the spectroscopy. This is quite a slippery point. The other model is the no, random is that at one point you are, yeah, I mean, no, you are, it, no, I mean, in all times it refers to the fact that you were going to, I mean, this approximation is trying to, with respect to a reference state where you have the nucleus as a system filled in terms of orbitals up to a certain Fermi surface, then you can construct transforming nucleons in quasi-particles. You can sum up quite easily all one particle, one hole excitation with respect to its reference state. And I mean, in the way that it was solved at the very beginning, I mean, maybe in the 60s, I don't remember, or in the 50s, because I think that this method, the random phase approximation, was introduced in atomic physics, not even in nuclear physics. I mean, there was at that time in the a couple of equations that appeared, you could solve in terms of a phase that could be expanded and so on. But I mean, it's something that traces back. In fact, you can do random phase approximation, and the evolution is quasi-particle random phase approximation. That is one used in nuclear structure calculation. Then the other method is the interacting boson models. That is a model that is based on specific features that appear in terms of the shape of nucleons, and of nuclei, sorry. You can have a spherical shape for very stable nuclei. Then when nuclei starts to be somehow the role of the proton-neutron interaction starts to be very important. Remember yesterday I spoke about this concept of exotic nuclei. Then what happens that the nucleon starts to be deformed, okay? And all the shapes that appears between a fully deformed shape and intermediate, then they give you rise, they rise to a specific symmetry, okay? That in terms of the sorry, I forgot the. You can use the algebraic properties of each kind of symmetries that corresponds to different shapes in order to construct a model where all the nucleons are paired to are paired somehow in terms of angular momentum I equals 0, 2, and so on. Okay, because of the generalized Pauli principle. So paired nucleons, couples of nucleons, they are bosons in terms of statistics, okay? So that's why you transform a system from a fermionic one into a bosonic one, and makes life easier to solve the equation, okay? And this is a very powerful one, but I mean, in terms of correlation, also this model is very, very poor. And that's my opinion, why these models like IBM, QRPA, and so on, they provide larger nuclear matrix elements. Okay. However, the models that I want to focus on they are the microscopic nuclear models. Microscopic nuclear models are intended like the nuclear shell model, or the so-called ab initio. English people, they say ab initio. I'm Italian, I speak Latin, and I say ab initio, okay? These models are based essentially on the main microscopic nuclear model. When I say microscopic, I mean that the degrees of freedom that you are counting for, they are not boson couples or quasi-particles or an energy density functional. They are the degrees of freedom of each nucleons, okay? So microscopic models are those where you account for the degrees of freedom of each nucleus. Its total angular momentum, orbital angular momentum, and so on, okay? The energy of the single nucleons and so on. And all these methods are framed in the, let's say, the father of this microscopic model, that is the independent nuclear shell model. Okay. Let's keep this in mind when I'll come back to the discussion about what are the main issues dealing with the microscopic nuclear models that are the ones that obviously they should give us more predictivity in terms of the nuclear matrix elements. And I want to first to complete my discussion about the calculation of some quantities inside that expression. Namely, there is, since all these models, they deal with a situation that is very complicated to construct all possible intermediate states of the daughter nucleus and calculate those summation, okay? Then what happens that in most of calculation, apart from QRPA, where it's easy to construct a large number of intermediate states of the daughter nucleus, deals with with something that is called closure approximation. I don't know how many of you work at least in experiment in the detection of neutrinos double beta decay, but maybe reading some theoretical papers you have met this concept. Namely, what happens is that inside that denominator, okay, the quantity that deals with the energy of the intermediate states and okay, and the energy of the parent and granddaughter states, this may be approximated as an average value. Okay? An average value that can be reasonably evaluated in terms of the density of intermediate states that appears in the granular nucleus, because you have to know that for this nuclear system there is a density of intermediate states that in terms of energy can be almost constant. Okay, so one may evaluate EK using an average value. Then what happens is that inside, if you substitute inside your integral this quantity with an average value, now the summation does not depend any longer on the energy of the intermediate state. Then in the above expression, you can you are no longer constrained by the integral, okay, that appears in the matrix element, and you can use the closure property of the intermediate states. Then what happens that you move from a summation over K of the one body density matrix elements into a two-body density matrix element between only the final and the initial state. So that in our calculation, nuclear structure calculation, we don't need any longer to worry about the calculation of all intermediate states of the daughter nucleus. Okay? This is a simplification that is something, first of all, the dependence on this average value is quite very weak. So, I mean, if you use a reasonable value, you see that difference of a few MeV doesn't change your results in the end, okay? Moreover, this is an approximation that works for neutrinos double beta decay, because usually for the neutrinos double beta decay, as mentioned by Claudia yesterday, you are dealing with an exchange momentum that is about in the range between 100 to 200 MeV. Okay, correct? So this makes this approximation a good one. Why I'm telling this to you? Because eventually, if you are dealing with the double beta decay but with the emission of two neutrinos, the expression of the matrix elements is similar. It appears again that denominator. But in that case, the momentum is no longer so high. It's a small one. And then this approximation, eventually, if you want to apply closure approximation to the calculation of the two neutrino double beta decay, this approximation is quite bad. As a matter of fact, the comparison between the exact calculation and the one that you use closure approximation for two neutrino double beta decay, the difference can be a factor of 5, 6, 7, something like that. While in now we are able, for example, in nuclear shell model, able to manage for calcium-48, you can get rid of this approximation. And the comparison between approximation and full calculation, it's the difference is less than 10% on the matrix element. So this is a good approximation. Okay. This is this is the first issue that I wanted to point you out. There is another point that I would like to consider with you, because come si chiude? No, forse qui. No, perché non... Scusami.
No, non so neanche io, guarda.
Prova. Ah, ecco. No, ok. Ok, thank you. Però, un attimo. Let me... Come torno sulla cartella, mo? Forse meglio interrompere e riprendere? No?
No.
Allora, se... Ok. Perfetto, chiudiamo. Perché io volevo... ok. Ok. Come si fa a ingrandire? Oh, scusami. Questo come devo fare?
Aspetta, non ne faccio stampare.
Sì. Ah, ok.
Così?
It's enough. It's enough. No, it's enough. Ok. Now, I want to tackle, excuse me, who was that asked me how does this form of the potential impacts on the calculation of the nuclear matrix element? Someone asked. Yeah, that's my point. Now, let's look to, no, what I did. Sorry. Aspetta. Ok. Mo il pointer qual è quello sopra? Ok. Ok. In this plot, I've reported here you see this is the two nucleon potential like the one that I've draw here. Okay. Now, what happens if you have a potential that is a strong repulsive is infinite, positive infinite? Then it means that the true nuclear wave function, okay, should be zero in this short range, correct? So psi, capital psi, is my total nuclear wave function, the real one, the one that should be zero here. Now, nuclear models that I mentioned you before, they are constructed, the nuclear wave functions, they are constructed in terms of a basis where they do appear some uncorrelated wave function, namely functions that are regular in this region, they are different from zero. Okay? So what happens is that in such a case, you have that you need to construct effective nuclear wave functions in order to consider that the real one is equal to zero in this range. Okay? Is it clear? Please, if it's not clear, please ask. So you need to construct an effective wave function, an action that takes into account of the fact that the basis, the wave function that you can construct in terms of your nuclear model is a non-correlated one, while the correlated one, the one that works, should be zero. So usually this means that you need to renormalize your potential somehow. The matrix elements of your potential should be constructed as effective matrix elements. Okay? So one of the most famous application of this concept to two-body potential. Maybe you have heard about the so-called Bruckner reaction matrix, the so-called G matrix. None of you. This is something that every nuclear theorist knows quite well, because I mean this has been the only way to deal with the two-body potential for something like almost, still people, they are using the G matrix. I mean, so it's about 60, 70 years that people that are doing this, okay? What they do is to construct an effective matrix elements, okay? Well, but this also means that you need to translate the action of the effective operator on your matrix elements, this one. Sorry. On this matrix elements. Namely, you need to include what in jargon is called, you need to include a short-range correlation in the definition of these matrix elements. That accounts for the fact that then this wave function, that the nature of the nuclear wave function that appears in the calculation of the one or two body matrix elements, okay, is consistent with your transition potential, transition matrix element. Is it correct? Is it clear what is this problem? You need to match the fact that this, they don't take into account, they get rid with a correlated with function of the problem. You need to find somehow the fact that the nuclear wave function is zero in that region somehow. If you don't take into account here, you need to take into account this here. Yeah, namely, as I will show you, need to introduce some kind of a cutoff. Smooth your matrix elements. Yeah, it smooths your potential, correct. But you cannot see this here. Use this smoothing of the potential, you need to see this one here. Okay? I don't know if you, no, because I mean, it's complicated in a few minutes to do all the Bruckner theory and show you this, I mean, okay? Namely, let's call G, how is it called? The reaction matrix. The action of the G matrix on the correlated wave function is equal to the action of the potential on the true wave function. Okay? And you need to reply this action operator on this guy. Okay? I know that it's a complicated concept, but this is a true problem because the evaluation of this short-range correlation impacts about up to 10–15% on the value of the nuclear matrix elements. Okay? And there are several other problems. Namely, what you are doing is to convolute the neutrino potential you define a new neutrino potential, U, from your original one, in terms of some functions that are called the Jastrow function, who take into account of this action on the potential. if you apply this function to V, you get G. Okay? In very, very, very raw terms. This is in momentum space. If you do this convolution in configuration space, in R space, then this function are expressed like this: 1 minus C e2 minus A R squared, 1 minus B R squared. Okay? They appear three parameters, A, B, C, that are constructed in order to fit this Jastrow function, namely the action of your G matrix. Okay? They are tuned in order to have to obtain the same action of the G matrix. This is a very simplified. Obviously, these are approximation. Well, let's say that if you introduce more parameters and a more complicated expression, you get a better. You need at least, let's say that in order to have a reasonable description of this action, you need at least 3. Okay, that's the common action that should be done. Now, the point is that, however, this expression of the short-range correlation, that now it will appear here in this integral, okay, depends on the choice to renormalize the potential, namely geometric or more evolved approaches. There are new approaches. Geometrics is a very old one, but I mean, in the last 30 years, some other kind of, we have evolved this, the process to renormalize the two-nucleon potential, okay? Not only, but it depends on the nature, I mean, who is your choice of the nucleon potential. As I told you, the nucleon potential, you can locate a class of on-shell equivalent nuclear potential. But this means that then the parameters, they depend on your choice. So this is another uncertainty that comes out that can be evaluated in about at least 10%. Yeah. But I want to point you out another thing, that most of the calculation, yeah, take into account of this, but they don't start from this realistic potential in the construction of the nuclear Hamiltonian. Namely, if you are doing, for example, interacting shell model, in the interacting shell model, the parameters that appears in the definition of Hamiltonian could be fitted in order to reproduce at best the spectroscopic properties of a certain region. But this means that you don't start from the normalization of the potential, then the construction and effective many-body Hamiltonian, and so on, so on, so on. Something, this is a very long process in order to be consistent. So sometimes you introduce this because you know that you need to catch somehow this integral, but you made a choice. So that's why usually in theoretical papers, they are reported different values for different choices of the short-range correlations. Okay? I want to point you out that this trouble does not appear if you start from a smooth potential like the one that come from the chiral effective field theory. There is no longer this problem, so you get rid of the short-range correlation. Okay, so the new frontier doesn't care about this. But this is something that we are doing in very recent years. I mean, I'm speaking of current undergoing research. Yes, yes, but let's. No, yeah, you are completely right. It means that you have extra terms in the Hamiltonian, but also extra term in the definition of the nuclear matrix element. And this is something that we are just starting to do. Hopefully, these extra terms, they should be less relevant, but this is something that we didn't yet evaluate. Okay? This is current research. Okay? But I want let's be let's stuck only to the what is standard. Is shared in most of the community of people doing neutrino double beta decay and calculation of its matrix element. Okay. Oof, okay. Now. Okay. Now. Uh, Now I would like to discuss a bit about the microscopic models, if you don't mind, because I want to come out with some points that deal with the so-called canching of GA problem. Okay, but in order to do this, I need to give you some hints how you construct a microscopic models. Otherwise, could be complicated. Okay. Uh, if you are not familiar with the independent nuclear shell model, as I mentioned yesterday, the independent nuclear shell model comes out from the fact that we observed that in correspondence of some specific numbers of neutrons and or protons, nuclei present some specific properties of stability, smaller radii, more binding energy, and so on. Okay, so it looks like nuclei behave like atoms, where you have the so-called noble gases that exhibit the same feature at a certain value of the number of the electrons. Okay, so it means that you can introduce a nuclear shell model. And nuclear shell model means also that you are introducing in the expression of your Hamiltonian, nuclear Hamiltonian there, an extra term that is in auxiliary potential that should absorb the most of the role of the two-body and three-body terms. Okay? Namely, you write your Hamiltonian as this one. In terms of an auxiliary one-body potential U. Okay. Then at this point you have a new one-body Hamiltonian that I'm going to call H naught plus a residual two-body term. Okay. The independent nuclear shell model comes if I make a good choice of this auxiliary potential, then this one could be residual, then I could neglect it. Okay? And then I have only one Hamiltonian, one body Hamiltonian, and the diagonalization of this one body Hamiltonian will give me a sequence of energy orbitals, like in the case of the atomic shell model. okay, that could be filled by the nucleus that belongs to the nucleus that is under consideration. What is the sequence? Maybe you have seen sometimes. Let me show first uh, uh, what we would like to have, and then I tell you what is the choice. Well, one thing that you should do is to construct this auxiliary potential, to an artifact procedure with your two-body potential. That would be the best. Unless the fact that this two-body potential is strongly repulsive and should be renormalized. However, if you do the renormalization through the Bruckner procedure, you go to what is called the so-called Bruckner artifact, and you can construct this one consistently with your starting two-body potential. But I didn't mention this this construction of the renormalization through the Bruckner procedure gives you the so-called Bruckner matrix, the reaction matrix that is energy dependent. So the life is a nightmare. Okay? That's why this is something that usually is avoided in the construction of the auxiliary potential. But looking to the energy orbital that comes out of the one that comes out from the observation of the physics of nuclei, you see that there is a sequence that is something. You have a orbital, a 0 s orbital, s1 half orbital here. Then you have a p3 half orbital and the p1 half. Then you have a d5 half, a d3 half, and a new s1 half that are able to reproduce the so-called magic numbers, nuclear magic number. So it looks like that's what usually people do. You need, it could be okay to use an harmonic oscillator potential, as usual, because people in nuclear theory, not in nuclear theory, sorry, theoretical physicists, they have always this trick, trying to fit everything inside the harmonic oscillator, because we know how to solve it and it's easy to be managed. Please give a look, but anytime you try to write your potential as a two-body oscillator, is it true or not? I mean, yeah, exactly. Yeah, yeah. Then you feel, let's say that you are considering, for example, helium-4. Helium-4 is 2 protons here and 2 neutrons here. Then you have the next magic nucleus is oxygen-16. Oxygen-16, you feel P3 half that can allow 4 identical particles, and P1 half that allows 2 identical particles. Same here. Then it looks like, I mean, it works, because then you have helium-4, oxygen-16. The other one is calcium-14, and so on, okay? So usually you have a parameterized harmonic oscillator as your choice. And it works, almost. What I mean, if you are doing independent nuclear shell model, this basis is not properly working, because the next orbital that gives you the magic number 28, is made by only the F7 alpha. Okay? So what you should add to an harmonic oscillator in order to work within an independent nuclear shell model is harmonic oscillator plus a spin orbit interaction. Because the spin orbit interaction that is not a relativistic interpretation, is stronger than the one in atomic physics, is going to split this orbital, okay, in terms of energy, and generate this single orbital shell made by the only F7 alpha. That's how Maria Goppelmayer got his Nobel Prize. Okay, no, it's worth to point this out. Yeah. Yeah, no, I mean, it's the same picture, okay? Okay, did you get how does it work, the independent nuclear shell model? Now, what you want is, however, to evolve your picture and to account for this, because this is a one-body problem somehow. But if you are going to consider the effect of your residual 2 or maybe 3-body force, then the degeneracy that comes out from such a picture is removed, and you ignite more correlations and a more realistic picture. Okay? So for example, since the two-body potential usually they contain a spin orbit term, the spin orbit will be accounted for from the two-body potential. Okay? So you can stick with wave function that are constituted as slated determinants of harmonic oscillator wave function, our uncorrelated wave function, the one that I mentioned to you before, okay? And then you act with your effective Hamiltonian, you get your eigenvalues. Now, microscopic models, they start from this picture, okay? But you have two ways to proceed. The fact that these closed shell nuclei are stable, they can let us induce to construct a scheme where you reduce your full space Hamiltonian for the full number of nucleons, freezing out the degrees of freedom of the core. For example, oxygen 18 is no longer this one plus 2 neutrons here, but it's just 2 neutrons in a reduced model space. And this can be diagonalized quite easily in terms of the degrees of freedom of your nucleons. Okay? Or what happens now with ab initio methods, you try to consider all degrees of freedom of nucleons and construct in an efficient way all the correlation that appears starting from the picture of the independent particle shell model. Namely, oxygen 16 Then you have this as a reference state, the core. Then you start to construct a series of particle Hall excitation. Let's say there is a particle that leaves the P1 half and jumps inside the D5 half or whatever. Okay? So in ab initio method, you start always from a reference state where you have filled some of your energy orbitals. And then you construct a new Hamiltonian where all particle Hall excitation are taken into account with respect to this reference configuration. This is, however, complicated because, I mean, this is an infinite problem from the computational point of view. Now, what they do ab initio calculation as well as the so-called realistic nuclear shell model. What you do is to employ some similarity transformation that transform the full Hamiltonian into a reduced one and then diagonalize it. Take into account with the similarity operation, similarity transformation of all correlation that did not be taken into account explicitly. I know there are many words. Namely, if I neglect some sort of correlation, this similarity transformation should take into account somehow. Okay? But you are able to construct an effective Hamiltonian that accounts also for what is neglected. But the effective Hamiltonian is different from the original one. You see my point? Yeah, maybe it's better you ask question at this point.
This is definitely not a unique procedure, right?
Obviously, there are different, you are right, completely right, because obviously different similarity transformation give you different, same eigenvalues, but different wave function.
So now, if we think about the eventual nuclear matrix element with the
Correct, but now, within using these approaches, that's the main point. You are able, because these processes, they are a theoretical one. You are not tuning matrix elements and getting a new effective Hamiltonian. You are constructing by way of, in a theoretical, by way of many body theory, namely the methods that I'm speaking, they are the so-called coupled cluster method. Or the in medium SRG, in medium similarity renormalization group, namely, you are using the techniques of the renormalization group in order to get a similarity transformation into in medium system, in medium SRG. This is the most promising of the ab initio. My personal approach, because I mean I studied this for a long time, is to construct a nuclear shell model effective Hamiltonian in terms of many body perturbation theory. These approaches, however, they give you the expression of the similarity or unitary transformation of your Hamiltonian. And with that unitary operator, you can construct effective operators. I wanted to show you more, but I think that my time is up, and I want to, however, maybe I can show you results of what happens if you are doing this for decays that are observables. Let me start from the first figure that worried Claudia, that is this one. No. Maybe I do not double click properly. No. Can you help him, please? We do faster. If you can open this one. Grazie.
Lo vedete?
Ah, it's on the other side. Oh, it was okay. Ah, can you shrink it? No, how do you? Ok. No, un altro po' perché si deve vedere l'asse delle X. Needs to. Okay, thank you. Yesterday, maybe some of you know about this so-called catching puzzle. They call it puzzle because people, they say it's this, it's that, it's something else, or whatever, okay, of the coupling, axial coupling constant GA. Please note that the catching of GA plays a certain role for beta decay, single beta decay. Namely, you need to catch, as you see, in these graphs, they are reported the results of calculations on the x-axis versus experimental one. And this correlation plot tells you that if you reduce by a factor about 0.7 the value of GA, you are able to reproduce in nuclear structure calculation the matrix elements of the observed beta decays. Okay? If you are dealing with the two neutrino double beta decay, GA plays a role as GA squared. In a neutrinos double beta decay, the role of this catch is a fourth. So 0.7 to the fourth is a, how can I say, is going to reduce your values quite a lot. So if we do not understand, or I mean, for me it's very clear what happens here. It's that you need to transform your matrix elements, this matrix element, not only with respect to the short range correlation, but also with respect to the action of the effective Hamiltonian consistently. Okay? But this is an old question because, I mean, if you consider that in nuclear structure calculation, no, there is not only GA effective, the catching, but we are using commonly electric charges of the neutron that are different from zero. And it's about 0.5. Or an effective charge of the proton is 1.5. So no surprise, because these deltas, they take into account of the neglected degrees of freedom that your Hamiltonian is not taking into account. Okay? So that's what you need, a theory that is able to consider this neglected and transform so that you don't need any longer to catch it, because the catching is coming from theory. In fact, please help me again. I'm going to show you some results of the ab initio calculation. Ab initio, thank you. If you can scroll a bit. Now, oh, sorry. These are done in terms of some ab initio models, okay. And there is the comparison between what happens if you do a proper calculation. As you can see, you don't need, in the comparison with the experiment, when you are including all the needed effective terms, that you don't need to catch GA in order to reproduce the matrix elements of beta decay. I have a, please, se mi puoi aiutare, scusa. Yeah, yeah. there is no need. But this is very well known. I mean, from old people. This is something that is only.
But from the outside, it's not obvious.
I mean, let me use this one. Yeah. These are our. Oh, so no, sorry. It's not this one. Close it here. No, if you close, yeah, okay. It's maybe this one. Okay, so this is a similar correlation plot of the previous one for nuclear matrix elements of 2 neutrino double beta decay that our group has calculated using the approach of constructing effective shell model Hamiltonian and effective operators from realistic forces, okay? So as you can see, if I don't use any effective operator, I don't reproduce the nuclear matrix elements, because reproducing nuclear matrix elements needs that those dots should lay on the bisect. Okay, but if you employ the correct, sorry, no, maybe I need to just to scroll. No, second, no, this is, okay, this is the page. Now they are reported in black. The dots where you employ the transition, the effective transition operator, then you see that you don't need any canching, because the canching is an effect of not using effective transition operators. That's it. So in order to take into account within your degrees, your chosen degrees of freedom that are reduced, otherwise you cannot solve the many body problem, of what is left outside. Usually people, they do it empirically, okay? But, I mean, now the theory has evolved, we don't need it any longer. That's the point. So there is no GA path at all. Okay? Any question? Because to conclude this, I want to show you another table in order also to show you that this means that for any operator, you need to calculate its effective one. And since people, usually what they do, as I said, oh, we need the canching of 0.7 for GA. If you employ it in the calculation of the neutrino nuclear matrix element, it's a nightmare. But this is not correct, because this canching cannot, I mean, the two processes are different, okay? They comes out from different physics. So you cannot literally use this procedure of using your empirical canching to calculate your neutrinos, or at least you do it because you cannot do better than this. But if you do a proper calculation, I want to show you this last slide. That should be, I don't know, maybe this one. No, okay, no, sorry. This is another plot where I show that using, but maybe. Okay, let's use this one, because at the end of this one I have what I wanted to say. No. Oh, maybe it's before. Okay, it's this one. This is an example where I'm used in the first table, no? Sorry, in the last table here. I calculated the neutrino double beta decay nuclear matrix elements M0 nu using canching factors that I have deduced from my calculation, the calculation that I showed you before for the 2 neutrino nuclear matrix elements. And using different Kenshin factors, because I get theoretical Kenshin factors that are different. 0.83 for the decay of calcium 48, 0.58, 56, 0.48, and so on, okay? Then I kench with this value my matrix elements, and you see that there is an impact that is up to minus 70%. Okay, but if you do it properly, namely you construct an effective operator for the neutrino stable beta decay, you see that the impact is that one above. There is a strong difference, for example, for the tellurium and xenon decay, because then the numbers, they change about 3%. Here they change, I mean, if you use the Kenshin factor, it's up to 50%. And the Kenshin factor is, that we found is similar to the empirical one, 0.7, about 0.7, 0.6. So you see, I mean, this is a good news for experimenters. Namely, you need to reduce your matrix, the theoretical nuclear matrix element, but not according to an empirical Kenshin factor. That's my point. And I have to tell you, now that ab initio calculation, they are starting, because ab initio calculations are much slower than the interaction model. We are converging also in the number. I mean the results we get for germanium there and those obtained with the first calculation of neutrino stable beta decay matrix element, they are pretty similar. Yeah. Okay. I think I could stop here, maybe because if you have any question. Sorry that I showed you so many slides in the end, but it was only to give you the feeling that doing the things properly with microscopic models, you can calculate reliable nuclear matrix elements, getting rid of an important effect that is this kenching of GA. Sorry? I mean, I started with the same Hamiltonian. I can show you that, yeah, spectroscopy is good. That's my point. Yeah, I don't want to make my own seminar, but I mean, obviously, what we are doing in our community. Let's change your question. Is to try to improve our approaches, microscopic one, in order to make our theoretical framework stronger, dealing with observables. Namely, since the neutrino stable beta decay is not yet observed, what we do is to look for observables that could be correlated with the calculation of beta decays, matrix elements, such as we have started to calculate the nuclear spectra, or another interesting phenomenon that up to now is not yet considered is the new muon capture. Why muon capture? Because muon capture, because of it's a beta decay essentially, but a Gamow-Teller transition, let's say, but it's a Gamow-Teller transition that deals with a particle, the muon, that is much larger than the electron. Then the range of energy of this process is consistent with the neutrino stable beta decay. And I mean, there is another point. I mean, all beta decay, all Gamow-Teller transition that we deal as observable, they are in a range of energy that is not one of the neutrino S1. So we need also to start to use this kind of observables in order to test, to validate our models. This is something that, apart from spectroscopy, because spectroscopy, let's say it's almost easy. I mean, this is more complicated somehow. Yeah, it's like yeah, it's larger than the it's this. In fact, you have not muon decay, you have a muon capture. That's why you need to consider. I know that we have spoken a lot about concepts that probably they were not in your courses. I mean, at university, and maybe many of these concepts are completely new to you. I tried to make it as simple as possible, but going more in deep in this, I mean, would mean that we need a few lectures, not just one lecture. That's a problem. I mean, this is a very complicated matter that has evolved in something like 70 years. So you have, I mean, it's difficult. And sometimes we are still using the basic tools that they were there 70 years ago. I mean, no question, no comments.
No, take the chance because Luigi has a train in about 2 hours. So
Yeah.
if you want to ask him if there's
No,
something.
I'm here. I mean, eventually. I mean, if you have no question now, but maybe during the coffee break. I mean,